Yeah. Good afternoon, students. Good afternoon to all. So I think all of you can hear me and see me, and my screen is also visible to all of you. Is that right? If I'm visible and audible, just type yes in the chat box or give me a thumbs up. Yeah, good afternoon. Good afternoon, Valmiki. Okay. Okay. Fine. So we'll start the class. Okay. So yesterday we have started this thermodynamics part, and we have discussed the basic terminologies that is being used in thermodynamics, and many formulas we have studied yesterday regarding the first law of thermodynamics, right? So first law of thermodynamics is related with internal energy, heat and work, right? And two properties we have seen: intensive property, extensive property, and two functions, state functions and path functions, we have discussed. So all the very basics things we have discussed yesterday. So coming to the today's session, so we are going to start with the heat capacity topic today. Okay, so today we are going to continue with the heat capacity. It is also one among the a topic of first law of thermodynamics only. So what is heat capacity? It is the heat required to raise the temperature of the system by 1 degree Celsius. If I want to raise the temperature by 1 degree Celsius, then the heat required to increase that temperature by 1 degree Celsius is called as heat capacity. Okay, it is denoted by the letter C. Its SI unit is joule per Kelvin. It is also an extensive property. Means on changing the size of the system, the value will change. The value of heat capacity will change. Okay, so it is an extensive property. And more C, more heat capacity means more heat is required to raise the temperature. They're directly proportional. C is directly proportional to the temperature. Okay. And coming to the formula that we have to use to solve the numericals, it is Q is equal to C into delta T. So heat exchange, the heat is directly proportional to the change in temperature. If you remove that proportionality symbol, we are introducing a constant called C, and that C is heat capacity, and C and Q both are giving one relation, which is Q is equal to C into delta T. So this relation is very important. Okay, this relation is very important. So this is about the properties and the definition of heat capacity. Now there are two types of heat capacity we have. Two types of heat capacity we have. Okay. One is molar heat capacity and the other one is specific heat capacity. So what is molar heat capacity? It is denoted by the letter Cm, and here it is denoted by the letter Cs. The heat required to raise the temperature of 1 mole of the system by 1 degree Celsius is called as molar heat capacity. The same heat which is required to raise the temperature of 1 kilogram of the system by 1 degree Celsius is called as specific heat capacity. Here mole and there it is kilogram. That's all. Okay. Coming to the properties of this molar heat capacity and specific heat capacity, both are intensive. Intensive means even if you change the size of the system or even if you change the quantity, the property will remain same. Okay, molar heat capacity of the substance will remain same and specific heat capacity of the substance will remain same. So they are intensive, and the SI unit for molar heat capacity is joule per Kelvin per mole, because it is for 1 mole, right? So it is joule per Kelvin per mole, and here since it is for 1 kilogram, it is joule per Kelvin per kilogram. Joule per Kelvin per kilogram. Okay. The formula, which is very important, it is Cm is equal to C by N. So in place of we are getting Q is equal to N into Cm del T. So we have got Q is equal to C del T in the previous slide, right? Now in place of C, we have to substitute N into Cm. In place of C, we have to substitute N into Cm. So we will arrive at this type of formula. And here Q is equal to M into Cs delta T. Okay. So all the three formulas are very, very important. So this is about Cm and Cs. So any doubt? from the heat capacity. So these are the formulas that you are going to study under heat capacity topic. This is okay. Shall we move on to the next formula? Shall I move on to the next topic? Say yes or no, students. Are you there? Yes, very good. Thank you so much, Valmiki, for your response. Yes, yes, good. Now coming to the relationship between CP and CV. Yes, good students. Relationship between CP and CV. So before moving on to this relation, there are two formulas which we have to study. It is QV is equal to NCV delta T and which is equal to delta U. The same way, QP is equal to NCP delta T which is equal to delta H. Okay, CP is the heat capacity at constant pressure and CV is the heat capacity at constant volume. Okay, constant volume gives us the internal energy change and constant pressure heat capacity gives us the change in enthalpy. Okay, now coming to the relationship between CP and CV, it is CP minus CV is equal to, actually CP minus CV is equal to NR, where N represents the number of moles. And if the number of mole is 1, for 1 mole of the systems, what we have to do? We have to substitute 1 in place of N, right? So it becomes CP minus CV is equal to R. So this is one of the previous year NEET question. Okay, NEET 2021 question it is. Which among the following is the correct relationship between CP and CV for 1 mole of an ideal gas? So this was the question and 4 options were given. So you have to select the correct relation. So nothing to do with the mathematics. No, nothing. Okay. So you're just going to find out the formula, which is going to give you 4 marks. Very easy type of question. Okay, fine. So with this, we will solve some previous year's questions of JEE and NEET from the topics that we have discussed so far. Okay, from the yesterday's topics and this heat capacity topic, we will discuss today. And after solving some questions, yeah, the difference is nothing but CP means heat capacity at constant pressure, my dear, and CV is heat capacity at constant volume, constant pressure and constant volume. It is not kind of a difference. This is different from that. Okay, this is in terms of pressure and that is in terms of volume. Okay, good. Previous year's questions we will solve. Why? Why means what I can say. Why in the sense what you're trying to ask? Yes, somebody have raised your hand. It seems. Okay, okay, okay. Somebody have raised your hand. Is there? Is that any doubt you have? Have raised your. Okay, if you're having any doubts, just put it in the chat box. Okay. Okay, we will go with I have taken for you. We will do it because thermodynamics is a physical chemistry, right? So we need to concentrate more on the numerical part. So that it solves the questions in the class, and that is the solve the board, and the weekend class Vivek's will cover. So the first question is the following object is the correct relationship between change in enthalpy and change in internal energy. Okay. This, while discussing this topic, I have told you that it was not the previous question. This was the question. This is the question. Options are given to you. Can you please find out the correct answer? If you have listened to yesterday's class carefully, if you have revised yesterday's concept at your home, yesterday or today, you might have given me the answer now. What is the correct answer for this? It's one of the formula. One of the formula which relates delta H and delta U. Which is the correct answer, student? Which option is correct? Try for it and give me the answer. Straightforward relation only. Sorry guys, just give me a moment. There is some server error it seems. So just give me a moment. I will, we will continue. Yeah. So, am I audible? Can you all hear me now? Everything is fine, right? Okay, okay. Thank you, thank you. So sorry, Mendes, there is some technical issue. It is showing some server error kind of thing. That's why this interruption has arisen. Sorry for that. Okay. Which is the correct answer? Some of you have given me the answer in the chat box. I think some of you have said it is option A. Very good. No, no, option C is not the answer. Option A is the correct answer. So yesterday we have discussed this. Delta H is equal to delta U plus delta Ng. RT is the correct relationship between delta H and delta U. Delta H is enthalpy and delta U is internal energy. Okay. So this is the answer. Very good. I don't know who have given me this option A as the answer. So good, great. Now coming to the next question. 1 mole of an ideal gas at 300 Kelvin is expanded isothermally from 1 liter to 10 liter volume. Delta U for this process is, and R value is also given to us. We have to find out the change in the internal energy, which is delta U. And volume. Volume is also given. Volume is given. We have to find out delta U. And the condition is expanded isothermally. Isothermally means, what is isothermal? Temperature is constant. If temperature is constant, delta T is equal to 0, right? Delta T is equal to 0. So these are the informations we are having with us. Now, how to find out delta U by using this information? Any idea? Has anyone got the answer? So just before few minutes at the last slide in heat capacity, we have seen one relation, right? Delta U is equal to NCV delta T. So this was the relation we have discussed at last now. Now here delta T is equal to 0 because the temperature is constant. Very good. Very good, Valmiki. Your answer is correct. Option A is the correct answer. Good. So let me discuss so that others also can understand it. Okay. Good. So delta T goes to 0. Delta T goes to 0. So 0 into anything is 0, right? So delta U is equal to 0. So option A is the correct answer. Very good. Option A is the correct answer. Okay, shall I move on to the next question? Is this clear for all? Just we have to use one formula, that's it. Shall I move on to the next question? Yes. Okay. Benny has raised your hand or what? Yes. Okay. Now coming to the next question, which of the following PV curve represents the maximum work done? How to find out the maximum work done from the graph? How to find out? We have seen this yesterday. So the maximum work done, maximum work done can be calculated using the area under the PV curve. Area under the PV curve. Or instead of this equal to symbol, I can put proportionality symbol. Okay. I'll put proportionality so that it will be more appropriate for you guys. So the maximum work done. Work done is directly proportional to the area under the PV curve. Very good. If the area under the PV curve is more, then the work done is also more. Now you can check for it. Valmiki, good. You are doing great. So here you see all the processes are isothermal and pressure volume curve is given. And this is the area under PV curve. And in case of option B, here is the area. And in case of option C, there is no area, only straight line is there. And in case of option D, this is the area. Okay. So option B only has the maximum area under the pressure volume curve. So in that case only the work done will be maximum. Okay. So option B will be the correct answer. Option B will be the correct answer for this question. Okay. Just use this relation to find out the answer. Shall we move on to the next question? Is this okay for all? Yes or no? Give me the response quickly. Okay, good. Which one among the following is the correct option for right relationship between CP and CV? For 1 mole of an ideal gas. So this was that NEET 2021 question which I was telling you while discussing the last topic. To find out the answer? Yes, good. Very good, students. CP minus CV is equal to R. Very good. Option C is the answer. Good, good, good. Fine. Coming to one more question. The correct option for the free expansion of an ideal gas under adiabatic condition is, which can be the correct answer? The correct option for free expansion. So what is meant by free expansion? In case of free expansion, the external pressure will be equal to 0. The system is expanding freely, so the external pressure is equal to, we cannot give some pressure and do the work on the system. So it will be equal to 0. Now we know that W is equal to minus P external del B. Okay, so this was a relation to find out the work done. And here we have got that P external is equal to 0, means the whole term will be equal to 0. Yes, Valmiki, option D is the correct answer. So P external goes to 0, so the work done will be equal to 0. Okay, work done is going to be equal to 0. So either option B or D should be the correct answer. And coming to the next given information, the system is adiabatic. The condition is adiabatic. Adiabatic means what? There is no heat exchange between the system and the surrounding. So what is heat exchange? Heat exchange is denoted by the letter Q. So that will be equal to 0 if the condition is adiabatic. Okay, because there is no heat exchange between the system and the surrounding. So Q is also equal to 0. Q is also equal to 0. Now, Q should also be equal to 0 and W should also be equal to 0. So that is given only in option D. So option D is the correct answer. Now, we will check this also. How delta T is equal to 0? That we will check. So from the first law of thermodynamics, we know that delta U is equal to Q plus W. And here, both work done and heat, they are equal to 0. So means delta U is equal to 0. So we are arriving at this type of equation. Now, when does delta U will be equal to 0? To know that, we have to use delta U is equal to NCV delta T relation. When this delta U will become 0? It will be equal to 0 only when delta T goes to 0. Will be equal to 0 only when delta T goes to 0. So that's why delta T is also equal to 0 for the last option. Okay. So in case of adiabatic condition free expansion, work done, heat exchange and temperature, everything is going to be equal to 0. Okay. Is this clear for all? Shall we move on to one more question? Yes? Yes or no? Have you guys taken down? Give me a thumbs up or Okay. Yeah. Good. Thank you, students. Under isothermal condition, a gas at 300 Kelvin expands from 0.1 liter to 0.25 liter against a constant external pressure of 2 bar. The work done by the gases. What we have to find out? Work done we have to find out. Okay. Under isothermal condition, gas is expanding against a constant external pressure. If the external pressure is constant, then it says that the process is irreversible. It says that the process is irreversible. Yesterday we have seen three formulas, right, to find out the work done for three processes. One is reversible, second is irreversible, and the third is free expansion. So now here we have to find out the work done for irreversible process. Okay. So to find out that, the formula says that, yeah, good, Balmiki. You have already solved all these questions or what? Giving me the answer so quickly, doing very great. So W is equal to minus P external V2 minus V1. So this is the formula to find out the work done for irreversible process. Okay. Now the external pressure, constant external pressure is how much? The P external value is 2 bar. It is 2 bar. And what is the volume? Initial volume is 0.1 liter. And this is final volume is 0.25 liter. Now substitute all these values here. It is minus 2 bar. And what is V2? 0.25 minus 0.1 liter. So it will give us minus 2 into 0.15 bar liter. And here the work done is going to be equal to minus 0.30 bar liter. But we have to find out the answer in terms of joules. Because in all the options, the answer is given in terms of joule. But we have got the answer in terms of bar liter here. So to convert this bar liter to joule, you have to multiply by the number 100. Okay, you have to multiply by the number 100. So 0.30 into 100 will give you minus 30 joule. So this is the work done in terms of joule. So it is given in option C. Okay, just we are taking this formula and substituting all the given values. So this is what you are going to study. You just need to take out the values that is given in the question. If you have found out those things, then by applying the formula, you can get the answer just by doing simple mathematics. That's all. Okay, physical chemistry is not difficult. It is easy. You just need to practice how to take out the given values and which formula you have to apply for this particular question. So to know that, you need practice. To know that you need practice, you have to solve n number of questions on that particular topic. Means at least you have to solve 5 to 10 questions on that topic in a day. Then only you will get used to it. Okay, just by practice only you can get the answer so quickly, and you will be able to know which formula have to be used for which question. Okay, otherwise it is going to be very tough only. Okay, if you are doing this, it will be the easiest part of your chemistry. So I hope this question is clear to all. Shall we move on to the next question? What do you guys say? Shall I go with the next slide? Yes. A gas is allowed to, yes, good. A gas is allowed to expand in a well-insulated container against a constant external pressure of 2.5 atmospheric pressure from an initial volume of 2.5 liter to final volume of 4.5 liter. The change in internal energy of the gas in joules will be. What we have to find out? We have to find out delta U. So how to find out delta U? We know that from first law of the thermodynamics, delta U is equal to Q plus W. So this is what the first law of thermodynamics says. Yes, good dear. Q plus W. And the question says that The container is a well-insulated container. Insulated means there is no heat exchange between the system and surrounding, right? So this statement gives us that Q value is equal to 0. So if Q goes to 0, then delta U is nothing but W. If you have find out this W, then delta U is also be delta U also are going to get from this. So what is W? How to find out the W? The same formula, minus P external delta V. So what is delta V? Minus P external V2 minus V1. So this formula only you are going to apply. So what is the external pressure value? Against a constant external pressure of 2.5 atmospheric pressure. So it is 2.5. Yes, option B is the correct answer. Good. 2.5 atmospheric pressure, and the final volume is 4.50 and the initial volume is 2.50. So if we do this, what we will get? We will get 2.5 into 2. So that will be equal to minus 5 into liter atmosphere. So this is in terms of liter atmosphere. Now we have to find out in terms of joules. So now here, to convert this liter atmosphere to joule, you have to multiply by the number 101.325. Okay. So this will give you the answer in terms of, so it is going to be minus 506.625 joule. Okay. Minus 506.625 joule. But the approximate answer is option B. Okay. We can approximate this to minus 505 joule, in which option B is the correct answer. It is the more appropriate answer. Okay. Option. Fine. The same formula we are going to apply. So since W is equal to delta U, here minus 505 is nothing but delta U. Okay. Now moving on to the next question. When 2 liter of ideal gas expands thermally into vacuum to a total volume of 6 liter, the change in internal energy is. Now for this question, there is no options, right? Means this is one of the JE question. So in JE exam, we don't have options for 5 questions, right? So this will come under that. For 10 questions, you won't be having options. So this is one of that 10. When 2 liter of an ideal gas expands isothermally, you have to find out the change in internal energy. The numerical type of question, we have to find out delta U. So how to find out delta U? So what are the informations we have? We have the volume, initial volume and final volume we have. And also the question says that expanding gas is expanding isothermally. Isothermally means temperature is constant. Isothermally means temperature is constant. If the temperature is constant, delta T is going to be equal to 0. So what we can do? Delta U is equal to NCV delta T. So delta T is going to 0. So delta U is also equal to 0. What is the answer? It is 0 joule. Answer is 0 joule is the answer. Okay, that is the nearest integer also. Okay. Shall we move on to the next question? Very easy, right? Very easy. Yes. Among the following, the number of state variables. Variable is nothing but state functions. Yesterday we have discussed, two types of functions, state functions and path functions. And here 4 terms are given, 4 functions are given to us. You have to find out which of the 4 functions are state function. Whether the answer is 1 or 2 or 3 or 4. Tell me. Start from internal energy. We have studied state function and path function yesterday. And in the path function, I have told you only 2 examples will come under path function. Who are those 2? One is heat and the other one is work. Only these 2 terms will come under path function. The remaining things, they are state function. Very good, Anusha. The answer is 3. Only heat and work are path function. Other terms are state function. So internal energy is a state function. Volume is a state function. Very good, Valmiki. Q is not the state function. It is the path function. And enthalpy is a state function. So the total number of state functions are 3. Answer is 3. Okay, good, good, great. So we'll move on to one more question. So this is the last question for this topic. So with this, we will complete this and we will move on to the next topic. Okay. So what does this question says? For the reaction H2F2 giving H2 plus F2, delta U, change in internal energy value is given as minus 59.6 kilojoule per mole at 27 degrees Celsius. We have to find out the enthalpy change for the above reaction. What is enthalpy change? It is delta H. We have to find out delta H for this reaction in terms of negative minus kilojoule per mole, and R value is given. So which relation you will use? Delta U is there, delta H we have to find out. So what is the relation between delta H and delta U? Delta H is equal to delta U plus delta Ng RT. So this is the formula that we are going to apply. Got it? Now delta U is there given in the question, minus 59.6 kilojoule per mole plus delta Ng. So what is delta Ng? Change in the number of moles of the gaseous product. It is the number of moles of gaseous product minus number of moles of gaseous reactant. So by using this formula, you can get, yes, good, Balmini. This is the relation. Now, how many, all the reactant and product you can see, they are in the gas phase only. So we have two products and both are present at 1 mole only. So if you calculate the total number of moles of the product, 1 plus 1 is 2. Okay, minus reactant. Reactant is also in 1 mole only. So it is 2 minus 1. 2 minus 57.1. Very good, very good. 2 minus 1 is 1. So the delta Ng value is coming out to be 1 and R value is 8.314 into temperature. So temperature, you see, it is 27 degrees Celsius. But we have to find out in terms of Kelvin. So convert this Celsius to Kelvin. So to convert this Celsius to Kelvin, what we have to do? Add by the number 273. So this will give you 300 Kelvin. So substitute 300 here and we have to find out the answer in terms of kilojoule. Delta U is given in terms of kilojoule only. Yeah, very good. But R is given in terms of joule. So what I have to do? I have to divide this term, this R by 10 power 3, that is 1000. Okay. Now on solving this everything, you will get minus 57.10 kilojoule per mole as the value for delta H. So the answer is minus 57.10. Okay, good. So this is the formula that we are applying. So any doubt from this question? Shall we move on with the next topic? So like this, you guys try to solve more number of questions, okay? So we will go with the next topic. Just give me a moment. Yeah. Some of you have raised your hand. If you're having any doubt, just put it in the chat book. Just give me a moment. I'll just take the other PPT and then I will come to you. Just a second. Yeah. Yeah, good. So is my screen visible? My screen visible to all? Is my screen visible to all of you? Yes? Yes, okay. Yeah, the next part, the second part of this thermodynamics lesson is thermochemistry. Okay. Now in thermochemistry part, we are going to discuss thermochemical equation, his law, and some of the equations, the formulas related to thermochemistry, and the spontaneity topic, which gives you the second law of thermodynamics, and the Gibbs free energy and equilibrium constant. Okay, so these are the topics. We will see one formulas under each topic, and we will see some theoretical point of view of that particular topic also, and then we will solve questions from these 5 topics. Okay, so starting from the first, which is thermochemical equation. So in a thermochemical equation, before moving on to that, we need to know some terms. The first term is enthalpy of reaction. So the enthalpy of reaction is the energy change accompanying a reaction is called as enthalpy of reaction. What is that? The energy change accompanying the reaction. So for a reactant which is having a reactants and products, so A and B are the reactants, C and D are the product. Now for this reaction, if I want to find out the enthalpy of reaction, which is denoted by the letter delta HR, it is equal to the sum of enthalpy of product minus the sum of enthalpy of the reactant. Enthalpy value will be given to you in the question. Okay, you don't have to worry about it. Just apply this formula, product minus reactant formula you apply and get the answer. Okay, so this is a formula that you are getting from this slide to find out the enthalpy of reaction. Okay, now this is denoted by the letter delta HR I have told you. Now coming to the next term, it is standard enthalpy of reaction. So what is standard enthalpy of reaction? When all the substance are in their standard state, then the energy change or the enthalpy change for that reaction is called as standard enthalpy of reaction. And here you see, it is denoted by delta HR naught. So this naught, the 0, which we are putting as the superscript, that denotes the standard value. Okay, what is meant by standard condition? Temperature and pressure should be at 298 Kelvin temperature and 1 bar pressure. So this is the standard condition for a reaction. Okay, and some of the standard forms of some elements I will give you. Standard enthalpy of formation. Yeah, this is the standard form of some of the elements. So all these things are required to find out the standard enthalpy of formation. Now this is the third term. First is enthalpy of reaction, delta HR. Second is delta HR naught. Now the third is standard enthalpy of formation, delta HF naught. Delta HF naught. It is the enthalpy change for the formation of 1 mole of a compound from elements in their most stable state. Formation of 1 mole of a compound from its most stable state, or their standard state, or their reference state. All the 3 states are same only: stable, reference, or standard. If 1 mole of the compound is formed from its constituent elements, then we call that as enthalpy change for the formation of reaction. Okay, so for carbon, we have different types of allotropes, right, for carbon, but the graphite is the standard form of carbon. Okay, we have diamond, we have graphite, we have fullerene. So all these are the allotropes of carbon only, but graphite is the standard form of carbon. Okay, and for bromine, the standard state is liquid state, and oxygen, gas, iodine, solid, nitrogen, gas. For phosphorus, we have 3 different types of phosphorus, right? Red phosphorus, white phosphorus, and black phosphorus. Red phosphorus is the standard form of phosphorus. And for mercury, the standard state is liquid, and sulfur, S8, rhombic sulfur is the standard form of sulfur. Rhombic sulfur is the standard form of sulfur. So these are the 8 very important compounds with their standard form. Okay, so you can go through this slide, and with the standard enthalpy of formation, we will discuss some examples to understand this. So there is one reaction. Calcium oxide is reacting with carbon dioxide to give calcium carbonate. Okay. Now, the standard enthalpy of formation cannot be calculated for this reaction because Calcium carbonate is formed at 1 mole only. Only 1 mole of calcium carbonate only is being formed. But the constituent elements that are present in this calcium carbonate are calcium, carbon, and oxygen, right? The standard state of calcium is solid, and for carbon it is graphite, and for oxygen should be in gaseous form. These are the constituent elements of the calcium carbonate compound. But this calcium carbonate is not formed from calcium or carbon or oxygen. Instead, it has formed from calcium oxide and carbon dioxide. Carbon dioxide or calcium oxide is not the standard form of any of these three. Okay, so delta HF not cannot be calculated for this reaction. And one more example I will give you. H2 plus Br2 giving 2HBr. For this reaction, if you see, standard enthalpy of formation cannot be calculated because 2 moles, 2 moles of HBr is formed. So we have hydrogen and bromine. The standard state of hydrogen is H2 in gaseous state, and for bromine also Br2 in gaseous state. These two are the standard state of hydrogen and bromine. Okay. Now the HBr is formed from its standard constituent element only, but only 1 mole. The definition says that only 1 mole of the compound should be formed from its constituent element. Okay. But 2 moles of HBr is being formed. 2 moles of HBr is being formed here from its constituent element. So that's why delta HF naught cannot be calculated for this reaction. Okay. So what does the statement says? Only 1 mole should be formed from its constituent state. If any of this tries to fail, then we cannot write the delta HF naught for the given reaction. Is this concept clear to all of you? If it is clear, then give me a thumbs up or type yes in the chat box so that I can understand. If any of you are having any doubt, you can let me know. Okay? Okay? Fine. So shall we move on to the next topic? I think I can move on to the next topic. Just give me a moment. Just give me a moment. I'll be back to you. Okay, just give me a moment. Sorry guys. Sorry guys. Thank you so much for your patience. So we will move on to Hess law. So what is Hess law? How to find out delta H from Hess law? So the Hess law states that regardless of the multiple stages or steps of a reaction, the total enthalpy change for the reaction is the sum of all the changes. So there is a reaction. A is the reactant and B is the product. To convert A to B, I need delta H of an amount of energy. Okay. To go from A to B, I can use some other pathway also. I can go to C from A, then C to D, then I can go from D to B. Okay. So in this pathway also, I can find out the product. Okay. Now, the enthalpy changes that has accompanied all these reactions. If you sum up all those things, it will give you the delta H value. It will be equal to the delta H value. So regardless of the multiple steps or stages of a reaction, the total enthalpy change, which is delta H for the reaction, is sum of all the changes. Delta H is equal to delta H1 plus delta H2 plus delta H3. Okay. So this is Hess law, which is very easy. This is called as Hess law. Is this okay? Clear for all? Did you guys understood? Yes. The next topic is thermochemistry. So in thermochemistry, we will discuss some of the standard enthalpy of some terms. The first term is combustion. Standard enthalpy of combustion, which is denoted by the letter delta H C naught. What is delta H C naught? So how many terms we have discussed in thermochemistry part from the beginning? Can you guys tell me? First is delta HR, second is delta HR naught, Third is delta HF naught. Delta HF naught. Okay, these three terms we have discussed so far. And now this is similar to that, delta HC naught. The enthalpy change when 1 mole of the substance is completely burnt in presence of sufficient supply of oxygen. So we know that combustion is heating a substance in presence of oxygen, right? Now, if 1 mole of the substance is burnt, then we call that as standard enthalpy of combustion. Okay. Now, all the reactants and products should be in standard state for this. Pressure should be 1 atmospheric pressure and temperature should be equal to 298 Kelvin. Okay, if you are doing the reaction at this condition, then we can write the delta HC naught for that reaction. Now you see here C4H10, this is called as butane. So butane requires 6.5 moles of oxygen and it is giving 4 moles of carbon dioxide and 5 moles of water. And delta HC naught for the reaction is minus 2658 kilojoule per mole. Values given in terms of minus, you see, this denotes that the reaction is exothermic in nature. Reaction is exothermic. Delta HC naught is exothermic. Okay. Now the next term is standard enthalpy of atomization. Delta HA naught. What it is? Enthalpy change for the conversion of 1 mole of any substance into gaseous atom. 1 mole of the substance to gaseous atom. Product should be in gaseous state for this. Only the product should be in gaseous state for this. And here the process is endo. Endo means the heat energy is absorbed. Heat energy is absorbed. Okay. In the last slide we have studied combustion. Combustion is exothermic and atomization is endothermic. These are very important things you have to keep in mind. Now that is an example you see. Hydrogen gas is there. This is the hydrogen molecule. Okay. Now there is one bond between the two hydrogen. Now I have to break this bond. If I break this bond, what I will get? I will get two hydrogen atom. Right. Now the bond breaking is happening. Bond breaking, the energy required to break the bond. So the bond needs some energy. Okay. So that's why it is called as energy absorbed process, energy absorption process. That's why it is endothermic. So you see the value is positive. For all endothermic process, delta H value should be positive. For exothermic, delta H value will be negative. So 4 plus 435 kilojoule per mole of energy is required, needed for this hydrogen to get broken. Okay. Now here sodium. Sodium in solid form, it is getting converted to gaseous form. So the condition says that the product should be in gaseous state. Now for this reaction, atomization and sublimation, conversion of solid to gas is sublimation, right? So both are same for this reaction. Clear? Clear for all? So is the atomization and combustion, these two terms clear for all of you? Any doubt from these two? Any doubt from these two? No doubt? Shall I move on to one more term? Yes? Okay. Good. The next term is bond enthalpy. Delta H naught with bond enthalpy. The energy absorbed in breaking of 1 mole bond in gaseous phase is called as bond enthalpy. So here we are having chlorine molecule in gaseous phase and it is breaking down to 2 chlorine atom. It is breaking down to 2 chlorine atom. In this case, both reactant and product should be in gaseous state. For atomization, only the product should be in gaseous phase. But for bond enthalpy, both reactant and product should be in gaseous phase. So this is a chlorine molecule. I have to break this bond and this molecule should be in gaseous phase. If I break this bond, it will be broken down. And here also the energy bond breaking means it is always endothermic only. So bond breaking means bond breaking is always endothermic only. Okay. Bond formation will always be an exothermic process and bond breaking will always be an endothermic process. Okay, so that's why here it is plus 242 kilojoule per mole. So my voice is not clear to you guys. What about the other students? What about the other students? Is it the case only with JNV Ramnagar or for all? What about the others? It is clear only for Valmiki. What about the others? Mm, for Rajat and others? Can you guys able to hear my voice? Yes? Okay. Then I think JNV Ramnagar, you just check with your, yeah, it is clear for Veena, Mido and the others. Means JNV Ramnagar students have to check with your connection, internet connection. So I think there are some technical issues with your side. So kindly rectify it, okay? So what I was telling, yeah, we are discussing about this bond enthalpy. Fine. So it is a bond breaking process, so it is endothermic in nature. Now, if I want to find out the delta HR not from bond enthalpy, to find out the standard enthalpy of reaction using bond enthalpy, you have to use this relation. Okay, summation of bond enthalpy of reactant minus summation of bond enthalpy of product. So these two are the products and these two are the reactant. So bond enthalpy value will be given to you in the question. Okay, just add all the products value and subtract it with the reactant. You will get the delta HR naught value directly by using simple addition and subtraction. Okay, so just memorize this formula. It is reactant minus product. Okay, all the substance should be in gaseous state. That is very important. If something is given at liquid state, if HCl is present in liquid state, then you should not consider the delta bond energy value of HCl into the equation. Okay, you should not substitute the value here in this formula. So you should substitute only the compounds which are present in gaseous state. Okay, so I think this is enough for today. So tomorrow we will discuss the lattice energy, hydration energy, and the remaining part of this lesson. So in the thermodynamics today, we have discussed all the standard enthalpy formulas. Okay, so concentrate on it and study Hess law and thermochemical equation part. So tomorrow we will continue this, and tomorrow, not tomorrow, in the next session. Okay, that is on Monday. We will do this, and we will try to solve some questions from this thermochemistry part. Okay, so I think the session is very useful and clear to all of you. If you're having any doubts, you can put it in the chat box now. If there is no doubt, we can meet up in the next session. Okay, thank you so much for listening the today's lecture, students. Thank you. Bye bye.